if second node actually exists. Make sense? So the idea of this is P1, iterate P1 without altering it, and build up P2. Once that's done, we'll just do this, and then we go to the next node. So if we can subtract condition nodes here, what we'll get is one or two nodes that come out and get pushed into P2. Then we set P1 to P2. That stands for partial, by the way, so partial number 1. We switch back up here, and P2, partial 2, becomes empty. We iterate the partial 1, which we just had, but now we're iterating it looking at a different B node. We eventually apply every single B node, and what we've emitted at each step of this is only new nodes and occasionally second nodes that don't have anything in them that B node has in them, but still have everything else that node had in them. Right? If we succeed at implementing that, we'll get out here, we should get out a P2 that, or a P1 that actually is, okay, got it. So P1 is the result. That's how it works. So in order for that to actually be implemented correctly, what we need next is condition node, SMI condition, subtract condition node A from B, or A minus B, and we also want the arena still. Okay, so now what we want to do is we want to figure out if anything in A and B overlap. And if they do, we need to take them out of A, right? We need to we make a new node either way, but we're trying to figure out how to subtract one node from the other. So, looking at this here, if their inputs don't overlap, then they don't intersect. So we could start there by saying, let's look for their intersection of their inputs. If we find one, then we have something useful, and we want to okay, got it. Then we want to determine if we need to split this into 2 nodes to output or 1 node to output. If this comes back empty, then we just output an exact copy of A with no alterations. New node comes back as null, then we actually emit nothing for that stage because the whole node got subtracted out. So input intersections, I32 intersect input intersection count. Okay, so we should end up outputting no more than one character for every character in A, and we don't have to do any extra iteration after that. We only need to determine that it's an intersecting character or not. Then we can stop checking everything in B when we find that it does intersect somewhere. So that gives us the intersecting characters. Now, if the intersection is greater than 0, we do one thing, otherwise we do this other thing. We're going to go ahead and create a result node here. Now, if there's no intersection between them, then what I said we do is we create an exact copy of A. Right? We put it on the arena. We say copy struct into result from A, exactly as it is. The only thing we maybe want to do is we want to set results inputs equal to our input intersections buffer from up there, and then block copy a dynamic array into there from there by that many, right? Now, if we actually have intersections, things get more fun. So, the next question is, what does the flag situation look like between these two things? It could be, for instance, that their flags are in opposition to each other. They have non-overlapping flag pins. If that's the case, then we do an exact copy of A. So I guess kind of what I need to be doing here is saying non-overlapping equals false. And then we're going to be doing several different tests that find out that might be finding out that we're non-overlapping. And this down here happens if we're non-overlapping, right? And that might look like that. So here we go. We are non-overlapping if input intersection count is greater than 0, is equal to 0. We do not, these two nodes do not overlap if their intersection count is 0. Great. If, okay, I'm gonna have to do the thing where I rename everything and flip a Boolean. We are not overlapping. So, if we are overlapping, then we carry on to this logic here, which says, find out if we have overlapping flags, right? So how does that work? Essentially what we want to do is we want to find out, we already have the flags in A. Ah, shit, that's another thing I have to change. So when I copied that node, I did not copy its flag list, and I totally should have. So what we're actually going to need is just something more sophisticated. We're just going to need an SMI node copy, like condition node copy, right? And when we do that, we're going to just pass it the arena in A, and it's the job of that function to do all of this work. Transition condition node SMI condition node copy takes an arena and transition condition node. I'll call it node. Here's result. We copy everything into A. No, that's just dumb. Result, so result, yeah, first we need to do a copy of that loop there, so, or that list there, so node equals, we're going to call these, I don't know, flag nodes. Right? And each of these is a condition flag. So we start with the first flag of node. And for each one of these, we need to create a new flag. And we need to push that flag onto the results first flag, last flag list there. Right? So there we go. That copies the flag nodes. Then we need to, nope, don't do that. We need to copy, the flag count should be fine. We can just do it like this for funsies. Equals node flag count, input count, and then the results input we'll have to just allocate here to make it reliable and easy to use. So no more, oh, but we do get one advantage, which is we can combine that with that, which is basically a non-advantage, but it does mean that this is a nice little compact line of code here. And there we go. There's our node copier. All good. So if we ever have non-overlapping nodes come into this thing for subtraction, we just copy the node, and there we go. Now, if they are overlapping in their input section, like in their input field set of their sets, we then want to check if their flags are overlapping. Now, how do we check if flags are overlapping? So inputs is just an array of inputs, and the idea is that that array is a set. The way we are defining a set of flags is by saying if our list is empty, then we have the complete set of flags. If we define, for instance, a particular flag, then we're pinning that flag down, but all the other flags that aren't defined are free to vary still. So we are the set of flags, of flag value, like of values for the flag field, where that have no disagreements with our pinned flags, basically, right? We are the set of flag states of for the total, not just for a particular flag, but for the entire flag field, which is all of the flags. We are the set of all those states that do not agree with our pinnings of particular flags. So, what does that look like when we want to check if our set overlaps with their set? Our set overlaps with their set so long as we do not define any pair of at no point do we define contradictory flag pins. Then we overlap at some point. If I say, for instance, let me put this another way. If I pin down that flag 1 should be a 1, and you pin down that flag 1 should be a 0, then we will have no overlaps, because there is no flag state where the two of our pins agree with each other. Therefore, we have no overlaps. On the other hand, if we don't have any disagreements, but we don't have we will definitely, if we don't have any disagreements, we will definitely have an overlap. The question is just then figuring out how much of an overlap and what nature of that overlap is, like, right? What is the nature of that overlap, I guess I'm saying. And so if I'm saying all of my flags must have, all of my flag states must have a 1 in flag 1, and you're also saying that, then we have exactly the same flag states. Now that doesn't mean that you subtract away all the flag states that I have, because I might have inputs that are not, that intersection of inputs might not have all of my inputs in them, right? There might be members of the intersection of inputs, or there might be inputs that I have that you can't subtract out, and so then I would still have something left over, right? On the other hand, if, say, I had no flag pins, and you had no flag pins, and we had the exact same set of characters, no, sorry, we have the exact same set of characters, but you have one flag pin and I have none, then after this subtraction, I would inherit the flag pin that you have, but inverted, right? For those characters where we are intersecting. Yeah. So this might be a little easier for me to think through if I write it down real quick in like this. So what we're talking about is a node is essentially the set you get when you cross the set of characters. So this is like a set S crossed with, let's see, I'm gonna call this, if E is, yeah, so S, a set S crossed with, no, that's okay, that's why I can't use that. So a set F crossed with a set T, where F is a subset of S and T is a subset of, yeah, F is a subset of E, T is a subset of S, right? So F is that. F is the set of things you get when you take everything in this set and everything in this set and make one element for every pair that you can make out of those two things, right? So if I have, that's what a node type is. Now if I have like two different nodes, if I have A and B are both nodes, I'm trying to define node A minus node B. What does that look like? Well, in set notation, this is going to be, let's call this F A something something at cross T A something something, right? We need to figure out how this works. So, in the most general way I can write it, it's that minus that. And so then what it really becomes is we need to do a little bit of set theory rearrangement here, a little set algebra. So, for instance, let me do this by cases just to help me wrap my head around it. If TA is equal to TB, so the flags are identical, right? We both have the same flag set, then this just becomes, we'll call that like TX. They're the same thing. So then A minus B becomes FA minus FB intersected TX, right? Or multiplied by, or matrixed out by TX. So that any of the inputs that A has that B does not have are the only thing left over in the input set, but this set has remained unaltered. Does that make sense? I mean, it can't grow, so at most it could be TA, but I can't do TA minus TB here. It can't be this cross with TA minus TB, because TA minus TB would be empty, and that would be wrong. That would say that we have an empty set, and we don't. We have this set, which is the set of all the inputs A has that B does not have, and, you know, TA essentially. So I guess that's what it is, right? So this is the set we have if we subtract our input set and don't look at flags at all. We keep the same portion of flags, but all we have to do now is subtract out the portion of flags that are uniquely yeah, the portion of flags that are uniquely from B, if that makes sense. That might need to be TB minus TA though. So let me think this through. These are equal, so this becomes an empty set, so this subtraction falls away. So that particular case I had works. What about the case where TA equals TB? Wait, is that the one I just did? What about the case where FA equals FB? So now the inputs are the same and the flag sets are different. So that should result in A minus B equals, now we already did something just like this, it should be TA minus TB times FA, right? So these two are equal, but the flags that B has that A does not have get lost, and then all the inputs remain the same for those flags, because B can't subtract away those things, right? TA minus CB times FA, well, which equals FB, right? So this actually would be that. Now let me try making this explicit. So let's say FA has the inputs 1, 2, 3, 4, and 5, and that FB has the inputs 1, 2, and 3. And for good measure, I'll throw in a 6 as well, right there. Right? So then we can say, what does TA and TB look like? Well, let's say TA and TB are defined as letter things. So A, B, C, D, E, F, G, H, right? There's 8 of those. 1, 2, 3, 4, 5, 6, 7, 8. And then suppose TB has just the set A, B, C, D in there, right? So there we go. This is fully intricate. None of them are equal. These have an intersection but are not overlapping. These are completely intersecting. How does it all combine? Right? These are non-hierarchical, even though they're intersecting. These are hierarchical. So what happens? Well, if I wanted A minus B, first of all, A is the set of all pairs that start with one of these numbers and end with one of these letters, and B is the set of all pairs that start with one of these numbers and end with one of these letters. So why don't I just do this literally by hand first? The set A looks like this. A, B, C, D, E, F, G, H. Now I want to subtract out everything that occurs here. So 1A gets subtracted out. 1B gets subtracted out. 1C gets subtracted out. 1D gets subtracted out. 2A, 2B, 2C, 2D. 3A, 3B, 3C, 3D. So what we have left over, this was the rectangle stuff I was telling you about earlier, the 3 corners. This is exactly what I had in mind. So I'm glad that it worked out that way, because it verifies that I have thought about most of this problem the right way, even if I can't clearly see in my head this formula yet. Need to fill up that coffee before I do the next video. So, point is, what's left over, does it conform to this formula? Everything, all the F's, also all the numbers from A, 1 through 5, but not including the numbers in B, 1, 2, 3, 6 is also missing, times TA, which is this rectangle here. So we have all the numbers that are left over are 4 and 5. So this leaves me with the set 4 and 5, and I multiply by TA. So I have A through H because none of these got affected by the subtraction, since they are since B didn't contain any of those numbers, right? But then we have to subtract out from that. No, that's not right. Is that a union? Does that need to be a union? Union, every number in FB, 1, 2, 3, 6, no, that's not right, times the flags of A, B, C, D, E, F, G. So E, F, G, H did stay. This part is right. TA minus TB expresses the portion of the A flags that didn't get subtracted out, which is the height of this rectangle, but the across dimension there can't just be FB, because that would have told us that we needed a 6. So this actually needs to be like FB intersected with FA. And the point there is we're getting everything from... So the flags from TA minus TB are the E, F, G, H, that section there. So E, F, G, H crossed with everything in both FB and FA from the numbers section. No. No, that's just everything from FA, period. Right? So everything from FA E, F, G, H union all of the things from TA, which is A through H, crossed with the stuff left over from that. Okay, so that's correct, but it double counts this part, right? The union is hiding the fact that with this part, essentially we've added it from both sides. So if I didn't want to include that twice, I would need to... This is why there are two nodes, by the way. One of the nodes makes one of these rectangles, and one of the other node makes the other rectangle, right? We need two rectangles. Each node can be one rectangle, and there you go. So yeah, so one of these needs to have an intersection with the other thing, I think. So this here gives me all of the letters, all of the T parts from A, crossed with everything that A had that B, all of the numbers that A had that B couldn't take away. And this part gives me all of the numbers that A had that B couldn't take away. I want to have only those numbers that A had that B couldn't take away. That weren't already counted over here, and therefore I'm looking for just those ones which actually show up in FB2. Is that actually true? If I took something out of B here, right, if I took out 2, then 2 would show up here. It would extend this rectangle, which would work. Right, so that rectangle would become that, that, and that, and then it would go all the way down to there, there, and there, and I would only need 1 and 3. So yeah, that actually does it. This gives me two nodes, this node and that node, that I can compute directly as a single node. And it doesn't duplicate any of the information. So the other question is, so that's the set theory stuff worked out, the set algebra for subtraction of these like node things, where a node is inputs crossed with a set of fields. But then my set of fields is also not represented as a direct set. It's represented as the set T, or like I'm going to call this like a flag set, is represented by essentially I have a bit field that's like got, you know, 5, 6, 7, 8, right, 9, 10, something like this, right? I have some bit field, and my bit field can have 1s, 0s, or x's in it, and anywhere where I have an x, I'm just saying give me all of the, give me a set right? And so then the question becomes, if that's how I'm defining my flag set, how do I actually perform the operations that I need to perform on that? In particular, how do I do A minus B? I'm going to have to do intersection too, but how do I do A minus B between two flag patterns? How do I derive element O from ABCD WXYZ? That's the question, right? So let's think that through. If this and this are both the the full set, then this needs to be an empty set. So this right here does not answer the question, how do I create an empty set? But I actually could. So I actually kind of lied here. This is not actually what I have the ability to do. I have the ability to do all of those things and make empty sets. And the way I can make an empty set, there's a couple options. I could just not emit a node whenever I know that the set's going to be empty. I can also create two flag checkers, like two flag check nodes that are contradictory within the same node, within the same condition node here. And that would essentially be encoding that there are no elements that match this node, right? There are no bit fields that match this pattern. So, for the case where flag set element O is not the empty set, first of all, how do we know when it's the case that flag set element O is not the empty set? And two, what is it if it's not empty? So let's start with situation number one. This is the full set, and this is a fully specified flag. What is left over? I see. Yeah, that's not good. So what's left over is the following thing. It's a union between four things. It's this union this union this union this, right? See what I'm saying? There's no other way to represent this. I can't. Adding fields here like shrinks the set, and what I'm actually saying is, oh wait, these should be zeros and zeros. So this is the set of all things that have a 1 in the first spot, union with the set of all things that have a 1 in the second spot, union with the set of all things that have a 0 in the third spot, union with the set of all things that have a 0 in the fourth spot. That is possible to represent because we can do just a chain of 4 nodes that have each of these things set like this. But man, is that annoying and not ideal. That basically means that this concept of returning 2 at a time isn't real, just for starters. And yeah. So what's happening here is that our set is essentially like a d-dimensional cube, where each corner of the cube, each vertex of the cube in d dimensions, is one of the points in our set, like in our set of possibilities. And our subsets are subsets of those things. And we need to be able to do operations like subtracting and intersecting these things. And it turns out that if you're going to allow subtraction, like, you could say, look, we're only trying to represent sets as, like, you can take a full cube, you can take one edge, you can take one face, you can take any n-dimensional object and say that that is all the vertices connected to that n-dimensional object are the thing. So, like, what is this, for instance? This is saying, go to the portion of the cube space where the first coordinate, the x coordinate, if there's like an x coordinate, y coordinate, a z coordinate, and a w coordinate here, go to the place where the x coordinate is 1, right? Lock that in. The other 3 coordinates can still vary. So what we're basically saying is, if you think about it in terms of 3 dimensions, x1 equals 1 on a cube is the face that's like, there's a face there. If we have a unit cube, there's a face at x equals 0, there's another face at x equals 1. There's a face in the plane y equals 0, there's a face in the plane y equals 1, and so on and so on. So the fully unspecified thing is the full hypercube. With one field specified, we're specifying a plane, well, in 4 dimensions, that specifies a 3-dimensional space for these 3 things to vary in. This specifies a 1-dimensional space. In order to do that minus that, I have to essentially... There's no way to do that except something like this that does a union of those. Yeah. This is not ideal, man. I guess we can do that, but that's actually not that much better than the situation we were already in. So, I guess there's a couple questions that I could consider. There might be better ways to go about handling all this. So, maybe this is too much of a generic situation, what I'm trying to do. Maybe I need to restrict this whole peaking thing that we're trying to optimize out. We allow the model to have peaking, and I don't see any way to make it work, make it easy and reasonable to implement without peaking, essentially. But it should totally be possible in theory for there to be a state machine where we don't do any peaking and get all the same behavior. It's just that deriving that is involving all of this stuff. It gets like slowly closer and closer to the point where it seems like the only option that we actually have is to just go ahead and do a full set specification. So I guess what we could do, alright, here's one option. Maybe flag sets just shouldn't be done by this flag pinning method. Maybe that's bad. Maybe I should go ahead and lean into the fact that it's like, look, we're already doing inputs as these 16-bit things, and we create a list of all of them, and then pare it down. We're talking about a number of flags at like the number 9, right? There's 9 flags. So that's actually fine. We can do the set of all 2 to the 9 values. We would have to limit ourselves to 16 bits, or 16 flags in any state machine, or something like that. But that's not going to be the end of the world if we decide to go that way. And we could just create an array of these things the way we did with integers. I guess the only problem is that this is the opposite of the normal case, right? So the normal case with characters is that you have a handful of them. There's a few places where you have like half of them, and that's the most you ever have, right? Maybe more for fallback. So maybe you get close to having all 200 in a few places, but a lot of the time you're manipulating a set with 1 or 2 or 10 or maybe 50 characters in it, right? Here, almost every single case transition doesn't do a flag check, and the ones that do a flag check only are allowed to check one flag by construction. So the initial sets we start with will almost always be the full set or exactly half of the space. They'll never be less than half the space. See, the reason I'm not going straight for this situation, there's 2 reasons. One is because it looks like a lot here, but it's actually more than that because there's 9 flags, remember? So this would explode out to 9. The other is I still don't feel like I fully understand it. There's something about it that's confusing because, as I said that, bit about how many flags there are, I realized that this is not the common case. So what I actually need to understand is not how this works, because that might happen, but that shouldn't happen all the time. What I actually have to watch out for is what happens when I have like this, and then what happens when I have something like this, right? How do those behave? So this just becomes the set flag set xxx0, right? That's it. We just need to flip that one thing and say, okay, so we're the set of all possibilities minus the set of possibilities on that face. Well, that's just all the remaining corners are the ones that aren't on that face but are on the opposite face. Right? Not this, is just this. Now, in this case, I think what we end up with is this. Right? In a case like this, we end up with the empty set, which we've already talked about, the fact that we don't really need to even worry about the fact that we don't have a way to directly represent that, but we can just represent it by not creating the set in the chain of unions, like the node in the chain of unions that would represent if it comes down to it, right? And do other special case handling for like situations where it comes up. So, okay. We can do this, I think. I think this is going to be fine. It's not going to be super common that we've chained up all of these. Normally what will happen is we have either no flags or one flag, and we have to at most probably do one more. I mean, you could get into a situation where it chains a couple of times, where like that hits, and then finally this here hits, right? In which case we would end up in a situation where it's like that is equal to this minus this. And what is that? Well, that's just this again. Right? Am I missing something there? Because if we're only ever chaining one flag on at a time, it always just becomes that. It never does this. I guess you could end up in situations where you have one of these stored somewhere. So like we've optimized this thing to look like this, and then someone else flows into here and does the same thing, and they have to now deal with one of these blowing up for them. Maybe. But yeah, subtraction isn't actually that hard as long as you only are subtracting one flag. Like if you're reversing a pin, basically. You're saying, oh, you pinned that way? Well, then I pin it this way to be the opposite of the set of things you contain. You had that whole set, well, I have this. If you didn't end up needing to subtract this, yeah, you'd have to take one where you flip this and a separate one where you flip this. And that's only for the situations where you don't already have a flag that agrees, right? So if I see this, what happens? Well, I'm already limited to this situation, so I'm not going to say flip this to 0, right? See, normally what I would have to do here is I would say if this was all x's, this would become the flag set 0xxx union the flag set xxx1, right? So that's a way to represent essentially the complement of this. But then you have to remember that we're intersecting that with flag set 1xxx because we are subtracting that from that. So complement of that, intersection that is the same thing. And this, when it intersects with this, is going to become the empty set. And so we would just end up with that intersected with that. And when we intersect these two things, we just append their flags together like that. So, I mean, there's a couple of worst case scenarios that are linear in the number of flags you have in terms of how big they expand out a single thing. And those only occur in the absolute worst case scenario where all of these are pinned and none of these are pinned. If any pin that this has that corresponds to a pin that that has doesn't need to be emitted separately. And any pin, anytime we only have like one or two pins, we only emit one or two flag sets. I think this will be fine. So I'm going to go ahead with this. I do need to like write down essentially what this logic looks like for subtraction, and well, I guess I'll just leave it here for the next video and make sure to pull it back up. Yeah, this is fine. This will work. It does mean that the thing I did over here for like assuming there would only be two nodes is going to be wrong. So we're going to need to improve this. So here I said, give me the new node. That's just wrong. What I'm actually getting is a whole new condition set. When I subtract two nodes. And if the new set.count is greater than 0, we actually have work to do. And what the work we do is we take p2.count and we add in the new sets count. And then we have to do that thing where we append two ZDLLs together again, right? No, these aren't ZDLLs. These are SLLQs, I believe. Just remembered that I didn't do that count plus earlier, so that's good to get fixed. Yeah, all of this still needs to get revisited once we get everything else up and running for this system. This is quite the undertaking this part is, but I kind of expected that this would be the best part. I mean, this is the part where the optimization has to get done. Is the most. This is the most algorithm heavy part we have to do. Is figure out how to transform a state machine with like peaking on its input into one that has no peaking on its input. Subtract condition node, condition node copy, set subtract, set intersect. Okay. So yeah, a node minus a node is essentially taking one rectangular set minus another rectangular set. And as it turns out, while that can be expressed as just two rectangular sets union together, those two rectangular sets can't necessarily be represented. The flags for those two, like the flag sets in those rectangles, can't necessarily be represented as just one flag, like as just one list of flag pins. They might need to be expanded out more than that. So here we go. We are saying, compare that to this code that we already did the same thing with. So p2 dot last next equals new set dot first prev equals p2 dot last p2 dot last equals new set dot last, and then finally p2 dot count plus equals new set dot count. And that just puts this new thing here onto p2, and we can forget whatever new set was then. Right? So once this loop is done, we've built up an entirely new p2 that breaks down all of the nodes that used to be in the original P1. So whatever P1 was, we broke down all of its nodes using all of the B node, using the particular B node, and then we repeat that process over and over again, applying each B node to the set until we've torn up the set into a bunch of separate nodes. In all likelihood, this will probably produce sets with 1 to 2 to 4 to 6 to 8 nodes at any given time, but you know, there might be a few cases where it blows up, but I'm expecting that we're dealing with like 4 or 8 things, right? It's actually not that crazy. It's just the amount of like the limits of what this has to be able to handle are much farther than the common case, so it makes the code look more pessimized than I think it actually is. Okay, so we're gonna wrap this one up pretty soon because we're almost twice as long as the previous episodes at this point, but we had a lot to get through there. I want to just finish strong and at least get the subtract condition node implemented, even if we don't get a chance to do any of the intersection stuff. So let's see if we have 20 minutes before this becomes a double-length episode. I'll try to split it up into 2 parts when I upload it or something. But here we go. Let's get this thing done. Okay, so we want to first figure out if we're checking to see if the subtraction of A minus B on the flag set is going to be an empty set. So the way that needs to look is as a loop over the nodes of A, and then inside that a loop over the flags of B. And now when I said flags of B, I meant the B flags, not the B flabugs. So little error there, no big deal. Also not the transitions or the flubug in that part was valid. Shouldn't have done all the A's to the B's with that many A's sitting around. That's just annoying. I have to figure out a way to make 4coder not do that. I want it to like treat that as an independent character, but not that, and it's some sort of in-between problem. Anyway, I mean, there's an obvious way to do it. I just haven't done it yet. Anyway, so we want to see if A flag equals B flag and so they are at the same, they're both referring to the same flag, and they do not have agreeing values, then these have conflicting pins, and we can double break. And that's not a feature of the language. So instead what you have to do is take your double break statement, stick a goto at the beginning, and then explain to the compiler where you meant double break should land you. Okay, and then